All right, well then let me go ahead and start sharing my screen, and then we'll continue where we left off. Okay, hold on. Sorry, with the new setup, I need to figure stuff out. Everyone can see my screen now? Okay, cool. All right, here's where we were when we left off on Wednesday. We were talking about potentially doing a singular perturbation analysis on the Navier-Stokes equation, because we're going to look at the inviscid flow limit. So in the limit where the inertial term, in large Reynolds number cases where the inertial terms could potentially be much larger than the viscous terms, right? And I asked you guys to kind of bear with me a little bit because we're going to, instead of thinking about the Navier-Stokes equations, which tell us about how velocity is going to be, or which governs velocity in our fluid flow, we're going to be thinking about vorticity. Now, we introduced vorticity a little bit earlier in the class. But you'll see now, hopefully today when we close the loop, that the vorticity way of thinking about stuff really is very important in inviscid flows. To get there, basically, we took the Navier-Stokes equation, and then through applying various identities, this is where all that stuff that we did in homeworks 1 and 2 and index notation and stuff really come in, because we actually were able to derive some of these identities. One of these more recent identities you actually just derived for homework 6, right? And then through things like substituting it in and then taking the overall corollary equation, we basically achieved something in the Navier-Stokes equation, or directly as a consequence of the Navier-Stokes equation for vorticity. And that's what this guy is right here, right? And it turns out that we have already thought a little bit about this vorticity equation, because if you recall from Stokes' first problem, we basically showed that vorticity kind of is like a mass transport problem. In this Stokes' first problem, or in our similarity solution, if you recall, the effect of this plate that suddenly started moving to the right at a speed of u was that the velocity of the fluid would slowly catch up, right, and then extend farther out into the semi-infinite domain above the plate. If you were to think about this in terms of vorticity, the way that you think about this is that there's a spike of vorticity that happens near the boundary that then diffuses farther and farther into the fluid as if it were a mass transport problem, right? And the reason that worked is because if we look at the vorticity equation here, and you re-express it in terms of what you would get for just 2D flows, so the vorticity can only be in the z direction, then you exactly recover this sort of diffusion equation. Okay, and so we can think instead about transport of some sort of scalar quantity that you would call the WZ in this case, that then moves, then carried through the fluid and governed by the vorticity equation. Okay. One lesson that we learned from this that sort of serves as a preview for how this connects to inviscid flows is that basically viscous stresses create vorticity, right? Because what's basically happening in this case, we have this plate that suddenly moves to the right, and that causes a lot of viscous stress that happens right at the surface of that plate, right? And that causes a big spike in vorticity. That's where this initial spike comes from, that then starts to diffuse away, right? The other forces that happen in our problem, the classical other forces like pressure and gravity, right? I'll just say, where are pressure and gravity? It turns out that those don't matter as much, right? And so here, I'll just go ahead and I'll just, instead of asking the question, I'll say pressure and gravity don't matter as much. Pressure and gravity do not influence vorticity. And the reason we can talk about this both intuitively and also mathematically. Pressure and gravity come about when we were deriving this. We got to this point right here, if you recall, right, where this term right here, which we called H, encapsulates all the effects of pressure and gravity. Okay, does it sound familiar at all from Wednesday? So we got to this sort of piece right here, pressure over rho minus GH plus 1/2 V squared. That was the H. And then once we took the curl of the equation, the curl of a gradient is always equal to 0. That was an identity that you guys derived in like homework 2 or something, right? And so mathematically, there's no way that pressure and gravity could actually influence vorticity because, well, the curl of any effect from pressure and gravity has to equal 0. Okay. The other way of thinking about this more physically and intuitively is that pressure and gravity are kind of like body forces, if you will, right? They act on the center of a fluid element. And vorticity doesn't care about that, right? Vorticity talks about how fluids rotate, right? How elements of fluids rotate, angular momentum and stuff like that. And if you have something that's acting on the center of a piece of fluid, then that cannot influence how it rotates, right? And so I'll say this, they do not influence viscosity because del cross del H is equal to 0, right? And it's because they act on the center of mass of fluid elements. So no effect on rotation. On the other hand, viscous forces do affect vorticity, right? And so that's sort of the connection that we need to get to when we start thinking about inviscid flows. This is why looking at vorticity is important. Because, so here, instead of talking about 2D flows now, I'll say this. So let's consider an inviscid flow. Okay, and obviously in an inviscid flow, that means that mu is equal to 0, right? If we let mu equal to 0, then if we look at this vorticity equation, what that means is that kinematic viscosity, which is just mu over rho, that is also equal to 0, right? So that means the vorticity equation becomes just these two terms. Let me write those down. Let me write those other terms down here, okay? So the vorticity equation becomes okay? Let's see what that means. This means that the change in vorticity of a fluid, remember this is the material derivative, right? And so this is just sort of, if you're looking at a fluid element and you're looking at how the vorticity changes as it moves along with the flow, right? The change in that vorticity is equal to omega vorticity dot del V, okay? What this means then is that if omega is equal to 0, somewhere in a flow, then omega equals 0 everywhere. Does that kind of make sense? Because if you are a fluid element, if you're an element of a fluid that's moving along, and initially your omega is equal to 0, right? Then this equation, in an inviscid flow case, obviously, right? Then this equation implies then that, well, omega is equal to 0, so that means your d omega dt, the change in your vorticity is also equal to 0. You start off at 0. If your change is equal to 0, then you're always going to be 0 everywhere. Does that make sense? Now, it turns out that in the problem that we started with a couple lectures ago for flow past an object, we have some fluid velocity moving past an object, right? So for flow past an object, it might make sense that vorticity is equal to 0 far from the object, right? In other words, over here, the fluid is not rotating. I'll just say flow, or I'll just say here is equal to 0 here, right? That kind of intuitively makes sense, right? There's no shear forces really when really far. You could imagine just some sort of uniform fluid moving. Okay? And so what that means is that in inviscid flow, in this flow past an object case, but this is true in many different cases, right? But inviscid flow is the same thing as an irrotational flow, as a flow where vorticity is equal to 0. Okay? So what this means is that inviscid flows are irrotational flows. Okay? Now, that's not true in general. Well, here's what I mean when I say it's not true in general. It's not true in the real world, because in the real world, there's no such thing as a purely inviscid flow, right? Basically, what I'm saying is this only works if your flow is truly inviscid. Right? In reality, as we mentioned above, viscosity, or I'll just say viscous effects, create vorticity at solid boundaries through the no-slip condition. Okay? But what this means is that our strategy should be that, if we're trying to find inviscid flows, maybe the right thing that we should be doing now is to actually look for irrotational flows, right? Flows where the vorticity is equal to 0. And it turns out that setting the vorticity equal to 0 is much easier of a way to solve a problem than it is to use the couple Navier-Stokes equation and stuff like that. Okay, and I'm going to show you a few examples of that. I'm just going to mention one more thing though. I'll say if indeed we have an irrotational flow, right? So I'll say flow is irrotational. Okay. Then once we get some sort of flow profile, it becomes really easy to figure out what the pressure and what the pressure field also looks like. And the reason why is because if you look at this sort of preliminary version of the vorticity equation right here, some of these terms are really simple to find out. Okay. So if we're talking about steady flows, then this term goes away, right? If our flow is also irrotational, then omega here is equal to 0, so this term also goes away. And this term also goes away, both because it's irrotational and also because it's inviscid, and so nu here goes to 0. And so what you're left with is del H equals 0, right? And del H equals 0 implies that this quantity right here is equal to some constant, right? Del H is 0, so this has no change, and so this is equal to some constant, right? So let me just write that down. Then omega cross V is equal to 0. And del cross omega is also equal to 0. Okay. And so what that means is that from the other preliminary equation that we had, which I'll just rewrite it right here. What we get is then okay. And I'll say this is 0 because it's steady. Okay. Now, if del H is equal to 0, what that means then is that okay. And again, this is true for inviscid rotational flows. Does anyone happen to know, has anyone seen this equation before? Does anyone know what this equation is called?
Bernoulli.
This is called the Bernoulli equation, right? Perhaps you saw this a little bit in undergrad, right? Basically, that this quantity is constant. And again, this is only true in inviscid irrotational flows. Okay. And so that's where we are at this point, basically. So to quickly summarize, what we've done so far is we found that at large Reynolds number, Navier-Stokes can be approximated by neglecting the viscous terms. And we need to do this in a singular perturbation analysis in the bulk solution, right? Far enough away from the boundary, right? What we also found by looking at the vorticity equation, so the vorticity equation, which is a direct consequence of the Navier-Stokes equations, right? This implies that irrotational flows are the same as inviscid flows, right? So irrotational flows are basically solutions to the Navier-Stokes equation when mu is equal to 0. Okay. And so what that means then is that if we're trying to find inviscid flow solutions, then we should look for irrotational flows, basically, right? So if we want to find inviscid to the Navier-Stokes equation, inviscid solutions to the Navier-Stokes equation, then we should look for that is terrible handwriting, for irrotational flows. Okay. And so for the rest of this class and maybe 1 or 2 lectures after this, we're going to get into basically how we're going to find irrotational flows. Okay. And so let me go ahead and go on to another section here. And the question is basically, irrotational flows. And it's how How do we find irrotational flows? Okay. One way of doing this is using something called a velocity potential. Okay. The way this works is we're going to define a function. We'll call this phi, or a field, I guess, right? This is a function of position, okay? It's a scalar function. Let me rewrite this here. I'll define a scalar field phi, and this is called a velocity potential. Such that the gradient of the scalar field is equal to a velocity. Okay. The reason why it's called a velocity potential then is it's kind of like a potential in an electric field or something like that, right? Or a gravitational potential. If you were to take a gravitational potential and then take a derivative of that, you know, the derivative of potential energy is equal to a force, right? That's basically what we're talking about here, right? In this case, the derivative of phi, of velocity potential, is just equal to the velocity itself. Okay. The reason we want to do this is because our vorticity then for the resulting velocity field, which is the curl of velocity, which is the curl of the gradient of phi, has to be equal to 0. This is an identity. The curl of a gradient is always equal to 0. If you don't believe me, we can just page 1. We can go to the previous page where we showed this from, or you can just look up your homework 1 or 2, something like that. Okay. By identity. Okay. And so what this means is that any scalar field phi can represent, not even can represent, I'll just say represents an irrotational velocity field. Okay? Because it turns out that, you know, if you just take a derivative to get the velocity field, then that velocity field by definition or by identity has to be irrotational because the vorticity is equal to 0 everywhere. Okay. The one caveat that we have for this is just like what's always been true for every problem that we've always solved, it must still satisfy the continuity equation, right? And if we just pick a random function out of a hat, a random scalar field out of a hat, and you take a gradient of that, it might not necessarily satisfy the continuity equation, right? And so we need to impose that as a condition for whatever phi we choose. Okay. So I'll say, but the velocity field still must satisfy continuity. Okay. Now the continuity equation obviously is del dot v is equal to 0. Okay. And so what that means is del dot gradient of our potential, or another way of writing this, I don't know what's going on with my pen today, I'm sorry. The Laplacian of our potential has to equal 0, right? And so this imposes a condition on our choice of phi. Okay. What this means is to find an inviscid flow, or I'll say find an inviscid irrotational flow, but remember inviscid and irrotational are the same thing now. Then all we have to do is solve this equation. Right? Once we solve this equation, then we can use this, the fact that the velocity is the gradient of the potential, to then actually find what we want, which is the velocity field, right? To find velocity. And we can use that equals a constant. Let me rewrite the word constant to find pressure. Okay, and again, this is called the Bernoulli equation, right? And so that's basically the game. Let me just take a quick step back, okay? The Navier-Stokes equations are very complicated. They're a set of 4 different coupled partial differential equations, right? And it turns out that solving 4 different equations is really difficult. And prior to all this, we basically were only able to solve the equations when we had unidirectional flow, where now basically 3 of those 4 equations don't matter, and we only look at either Vx or Vy or Vz or something like that, right? We could look at cases when we were almost in unidirectional flow, and then we can use some scaling arguments to show that still is only one of those terms one of those equations that really matters, right? But it turns out that if we're in the case where we have inviscid flow, so mu is equal to 0, then we actually don't need 4 different equations. Okay, we actually only need 1 differential equation. That's the differential equation right there. And once we solve this differential equation, then you can get everything that you care about. You can get the velocities, you can get the pressures, you can get how much force is required, is exerted on an object, all the classical things that we would ask you. You can get flow rates, all the classical things that we would ask you in a typical fluid mechanics problem. Okay? Do you guys want to see an actual problem then? Let's do an example. So you'll use this example a little bit in homework 7. So I'm not sure how far we'll get into it today, but let's go ahead and get going. So this is called inviscid flow past a cylinder. Okay. The idea here is we have a cylinder, so this is going to be a 2D flow. I think in the homework, we're going to ask you to look at what happens when we have flow past a sphere. But here we have some sort of fluid flowing past cylinder. It has a speed of u, okay? And the cylinder has a radius of a. Okay. Now, obviously, we're dealing with the cylinder, so perhaps it makes sense to use cylindrical coordinates. Okay. We'll give ourselves a set of axes here. We'll say x goes in that direction and y goes in this direction. Not necessarily that the origin is here. Instead, maybe it makes more sense to put the origin in the middle of the cylinder. So instead, perhaps it makes sense to use cylindrical coordinates like that. Okay. And so what we know is that the flow at r goes to infinity, that is that, right? Now, to convert this into cylindrical coordinates, again, it makes a lot more sense to try and solve this equation right here in cylindrical coordinates. And so let's do that, okay? To convert this into cylindrical coordinates, well, we just need to use the vector conversions and stuff, right? Okay. And so those conversions look something like this. We introduced this a little bit when we started when we talked about cylindrical coordinates initially, right? To remind you, in cylindrical coordinates, ER and E theta are basically in directions of increasing R and theta, right? And those aren't necessarily constant. Those are not necessarily constant quantities. They depend on where you actually are in the problem, right? If we're over here, for instance, like in this point where my mouse is, then ER is going to go in this direction, right? It's going to point towards the W, and then, or sorry, ER is going to point in this direction, farther away from the origin, and then E theta is going to point in this direction. Okay. Okay, but if we use these conversions, then what this means is that the flow at r goes to infinity now looks like this. V is equal to u times cosine theta of ER minus u times sine theta times E theta. Okay, and so what that means then is that VR is equal to u times cosine of theta. Okay, but of course the velocity is the gradient of the potential, the velocity potential, right? And the gradient of our velocity potential can be written like this. Okay, and so what this means is that because VR is equal to u cosine theta, then d phi dr is equal to that. Okay, everyone still with me? Likewise, v theta from over here is equal to minus, minus u sine theta. Okay, and that's equal to 1 over r d phi d theta. Okay. So what this implies then is that at r goes to infinity, phi can be written like this. If you don't believe me, do the derivatives. Okay, the derivative of phi with respect to r is u cosine theta. Okay, and the derivative of phi with respect to theta is minus UR sine theta, but then you divide by the R, and so you get minus U sine theta. Okay. This is sort of like a boundary condition that you could think of for what our velocity potential has to be. Remember, this is the original equation that we have, right? And this you could think about as some sort of boundary condition. Okay. And so now, basically, we need to solve for the velocity potential. Okay. That equation looks like this. Del squared phi, which in coordinates looks like this. Okay. We basically need to solve this differential equation. Now, given that our boundary condition as r goes to infinity looks like this, it might make sense. I'll just say, try a solution phi, which is a function of r and theta, like this, as some function f of r times cosine of theta. Okay. You kind of have a hint that this might be true because our boundary condition has something times cosine theta. Okay. If that's true, then maybe we can take this guy and substitute it into our differential equation. Then maybe we'll just get an equation for f, and then we should be able to solve that. Okay, let's go ahead and try that. Then what we get is del squared phi is now equal to 1 over r d by dr of r times df dr now. And the cosine of theta can come out, right? Because these derivatives are only with respect to r. We can do something similar over here. This gives us minus fr squared times cosine of theta. Because the second derivative of cosine, one derivative of cosine is negative sine, derivative of that is negative cosine, right? So that's where the negative cosine comes in. Okay, and then there's the f because you don't need to take a derivative of f with respect to theta. And this equals 0. Okay, luckily, it turns out our hunch here was correct. We can maybe cancel out a cosine theta from all the different terms. And then we'll expand this guy out and get something that looks like this. Okay, this is just product rule on the inside here, right? And then I'm just going to write it into a form that's even more tidy. Okay, that's a differential equation that we can solve, right? It's actually pretty simple. We are going to need boundary conditions for this differential equation. Okay, it's a second order differential equation, and so we need 2 boundary conditions, right? So let's find those boundary conditions. Okay. Can anyone guess what boundary conditions might be helpful here? Or where we should be looking for boundary conditions in this sort of problem?
Probably at r equals a.
At r equals a, right? Sounds good. What boundary condition will we expect at r equals a?
There's the no slip condition at the
There's some sort of no slip condition at r equals a, right? For reasons that I'll explain later, let's not deal with the well. So no slip will tell you that v theta is equal to 0. For reasons I'll explain later, let's table that for just a second. Instead, let's say Vr is going to be equal to 0. Okay, because well, by definition, you can't have fluid moving into or out of the cylinder. That's pretty simple, right? Okay.
Why are we having a no slip condition when we have vorticity at like an interface because of the no slip condition?
Yeah, so I'll get to that in a second.
Okay.
I'll get to that. Actually, I don't know if I'm going to have time to get to that today, but I promise you I'll get to that a little bit later. Okay. And so that's why I'm tabling the no slip condition at this point. Instead, I'm going to say at r equals a, then Vr is equal to 0. Okay. Now, of course, Vr, V is just the gradient of phi. And so Vr is just equal to d phi dr. Okay. Now, if d phi dr is equal to 0, then phi is just f of r times cosine of theta. And so this implies that df dr is equal to 0. Okay, that's one boundary condition. Can anyone think of a different boundary condition? We're going to need one more, right? Maybe not this time at r equals a, but maybe far away, right?
Yeah.
R goes to infinity.
Oh, sorry. Could we not just do like the same r equals infinity, but then say that f is just equal to ur?
Yeah, exactly, right? Because as r goes to infinity, we know that phi is equal to ur cosine theta, and we know that phi is also equal to f of r times cosine theta, and so therefore f of r has to equal ur. Make sense? So our second boundary condition is going to be this. F is going to be equal to ur. Okay. All right. Now we have a second order differential equation and two boundary conditions. Does anyone know how to solve a differential equation that looks kind of like this?
It's an equidimensional differential equation, so you can just use the change of variables with some variable equaling e to the r.
An equidimensional, I don't actually know what that means because I'm really bad at math.
It simplifies out to d squared f d squared phi minus f, where phi equals e to the r. And then you can solve it just by f equals, it should be like c1 r plus c2 over r.
So you're saying try something like f equals e to the r or something like that?
Plus, no, f equals c1r plus c2 1 over r.
Isn't that just method of undetermined coefficients?
You could also use that, yeah.
Okay, you guys are talking about a bunch of math terms that I don't actually know off the top of my head, and so I'm just going to tell you guys what I've been thinking. Try polynomial. Something like that, actually. Actually, I was going to just try polynomial. The way that that works, so I think the e to the r thing actually works if it's a linear differential equation. Or sorry, what they call it is a homogeneous differential equation where there's none of this r squared or r in front, right? Then you try e to the r, and then you get like a characteristic polynomial, and then you you try like e to the lambda r, and then you solve for lambda. In this case, actually, we got really lucky, and the powers of the r in front of each of the derivatives actually match exactly with the order of the derivative. And so the correct approach in this case is actually to try solutions like this. Try solutions of the form f of r equals r to the n. The way this kind of works, what's so funny? Okay, I'm just curious. I don't know. You guys kind of smile a little bit during this anyway. We'll go ahead and try solutions like this. And the reason is because for every derivative that you take, the n up here drops by 1. But then if you multiply it by the same order of the derivative, then you actually get back the same thing you get. And then that gives you an idea of what the n needs to be, right? And so let's go ahead and plug this into the ODE. Sorry. Okay. If we plug this into the ODE, then what we get is 2 derivatives of r to the n is n times n minus 1 r to the n minus 2, right? Chain power rule for derivatives, right? And so what we have is r squared times, like I said, 2 derivatives of this. And so you get n times n minus 1 r to the n minus 2. Okay. Next term is even easier. You have original r, and then the derivative of r to the n is just n times r to the n minus 1. And then the last term is even easier. That's just r to the n. That has to equal 0. And luckily, r to the n cancels out of everything here, right? This guy here gives you an r to the n. This guy here gives you an r to the n. This guy here gives you an r to the n. And so you have this I'm going to multiply out. So this term right here gives me an n squared minus n. Okay. This term right here gives me a plus n. And this here gives me a minus 1. That has to equal 0. Obviously, the minus n and the plus n's cancel. So you get n squared minus 1 is equal to 0. So that implies n equals plus or minus 1. Okay. And so then what you get is f of r equals some linear combination of our 2 potential solutions. And this might have been what you were talking about, Max. Maybe. I might have just transcribed what you were saying wrong.
Yeah, but it was a way more complicated method.
Okay.
So
okay.
It's good.
Okay, sounds good. But anyway, now just like before, we have 2 integration constants, and we need to find those using our boundary conditions. Okay, let's go ahead and do that. You might suspect then that boundary condition 2 implies that f is equal to ur as r goes to infinity. Notice how this boundary condition is actually a little strange, because like when r goes to infinity, then this means f actually goes to infinity. We're talking about the limiting asymptotic behavior as r goes to infinity here, right? And so what this implies then is that C1 is equal to u. Okay, it's kind of an improper boundary condition because everything is just going to infinity at that point. It's just how quickly does it actually go to infinity? Okay. Boundary condition 1, we need to talk about df dr. df dr is, well, C1 is equal to u, and so that's just equal to, the first term is just u, and the second term is C2 over r squared, and this has to equal 0 at r equals a. Okay, and so that implies, therefore, that C2 is equal to ua squared. Okay, and so this implies then that we have our f. F is equal to u times r plus ua squared over r. And so I just like to write things nice, neat, and tidy, like that. Okay. That's our f. Of course, we're interested in our actual velocity potential and then eventually our velocities, right? So let me go ahead and write those down. This implies then that phi is equal to u times r plus a squared over r times cosine theta, right? Phi is just f times cosine theta. And then we were interested in our velocity components, of course. And so VR here is equal to d phi dr. Okay. And so that's u times 1 minus a squared over r squared. And then v theta is 1 over r times d phi d theta. Okay, and so that's minus u times that. Okay, because the derivative of cosine is equal to negative sine. Let me make sure I'm not ambiguous. That's a 1 over r, not 1 over r squared. Okay, and that's our overall solution. We can do a quick gut check here. So like one thing that I always like to do at the end is just, you know, we can analyze the solution a little bit more. We can, for instance, ask ourselves, does this actually satisfy the boundary conditions that we imposed earlier? Okay, so does this satisfy the boundary conditions? Okay, right. So remember we had several boundary conditions. One was that at r goes to infinity, we have conditions for VR and V theta, right? Those conditions where at r goes to infinity, we have VR is equal to u cosine theta and V theta is equal to minus u sine theta. At r goes to infinity, here we have, well, when r goes to infinity, then this term goes away. And so we have VR is equal to u cosine theta. Okay. V theta, again, this term goes away. And so V theta is equal to minus u sine theta. So yes. Okay, yay, we got that one. All right. We also have boundary conditions at r equals a. At r equals a, let's look at this for a second here. VR is equal to 1 minus a squared over a squared, so 1 minus 1, and so that just gives us 0, right? So VR is equal to 0. So yes. Okay, but at r equals a, we also need to look at V theta. Okay, so V theta here, we have 1 plus a squared over a squared, so that's 2, right? So what we get is V theta is equal to minus 2 u sine theta. That's weird, right? You would expect that V theta should equal 0. That's a no-slip boundary condition, right? So the answer here is no. But maybe not to worry. We talked about this a little bit already, right? Our solution does not satisfy the no-slip boundary condition. And that's because mu is equal to 0, because it's an inviscid flow profile, right? There are several ways of thinking about this. One way of thinking about it is it's kind of like our singular perturbation problem, right? Our reaction diffusion problem, where when we set our epsilon to be really, really large, then the solution that we got was just that the concentration everywhere was 0, right? And we were unable to satisfy that boundary condition where the concentration is equal to C0 close to the edge of the block of catalyst. It sounds familiar to you guys, maybe, right? That's essentially what we're seeing here. Another way of thinking about it is this whole thing about vorticity and stuff, right? An inviscid flow, an inviscid irrotational flow cannot have viscosity by definition, right? Because the no-slip boundary condition is actually what causes vorticity to happen. If it did follow the no-slip boundary condition, then you would have some sort of velocity right here at the boundary, and then at the no-slip boundary condition you would have 0 velocity, and so there would be viscous stresses there, and there can't be viscous stresses in an inviscid flow, right? And so it's true by design that our inviscid flow should not be able to satisfy the boundary condition. Okay, we actually got essentially to where you guys need to go to get homework 7. I think we're going a little bit fast a little bit today. The one thing that I think you guys might need to do in homework 7, you can probably start problems 4 and 5 pretty easily at this point. The one thing that we haven't talked about is the pressure distribution. So we'll pick that up pretty quickly on Monday. Basically, how do we actually calculate pressure distribution? Just to give you a quick preview, you use the Bernoulli equation. You basically just use this, okay? And then the other thing that I'll do is, you know, I like to visualize things and stuff, and as you guys know. And so this gives you a VR and a V theta, but I really would like to be able to plot this and show you guys what the flow profile actually looks like. And so that's where we'll pick up. We'll pick up from on Monday. Okay. I'm going to take like a, I don't know, a 60-second break, and then I'll stop recording right now. And then after we get back, I'll talk a little bit about the exam. Okay. Go get up, go pee or whatever. Okay. I'll see you guys in like 60 seconds if you want to stick around.